Yeah, interesting this, because the first thing that Mike said when I came in today was, God, you're brave. There's a lot of people here who probably know an awful lot more about this subject than I do. So if you do, shut up and don't heckle, all right? If I got it wrong, shut up, I don't care, I haven't got time for this. The idea behind this talk came about because November before last I did a talk about how steam locos work. And then last year Mick and Mark did how electric locos work. And it occurs to me there's a lot of concentration on how locos work and not a lot about stuff underneath, how that works. So I thought it would be interesting to do that. So tonight I'm going to talk about things, boring things like this. Track gauge, the wheels, and why the rails are shaped the way they are. Talk more about the rails. What does the ballast do? All rails have ballast, do you know what it does? Some will, some won't. Chairs. Neil was very kindly brought in an old chair from the Southern Railway for you to have a look at. Likewise, what do the sleepers do? Talk a bit about rail path, traction, and then at the end, if I've got time, if I run out, I won't talk about it. It's about level crossings, because I find it quite interesting. I just want to start by defining what engineering is. Because I'm sure we've all got a very, very different idea of what engineering actually means. Yeah? Fundamentally, engineering is about problem solving. That's what engineers do. They have a problem, they produce something, design it, whatever it is, to solve that problem. Okay? And a lot of what I'm talking tonight is about the solutions that engineers have come up to produce or have produced to overcome specific problems, if you like. Now, there's a word in there that will scare a few people. I'm not going to talk much about maths. I've got a few equations, but they're very, very simple, and there's virtually no maths, all right? Even though a key part of engineering is maths. One of the things to understand about engineering is, generally speaking, engineering is all about evolution. Very, very rarely do you get a revolution. Someday somebody didn't sit there and go, oh, it'd be really good if we had rails. Nobody ever did that. Rails were evolved as a solution to a problem. So your cart goes down the road and sinks. How do I stop that from happening? Somebody developed some rails, fundamentally. But most of it's about evolution, and again, something that people just don't really understand enough about. So I'm going to start with railway gauge. So what is the railway gauge? The railway gauge is the distance between the inside of the rails. Okay? Not the outside, not the middle, it's the inside of the rail head. In the UK, it is set at 4 foot 8.5 inches. A nice round number. That is otherwise known as standard gauge. Okay? Now there are very many myths and untruths out there about how that number came about, but let me assure you it had absolutely nothing to do with the Romans. So, the first railways, or the first start of a railway, was actually what are called trackways. Typically you find them in a mine, you roll your wagon along full of ore or whatever and it sinks. So they put some rails on the ground to stop it from sinking. Like that, yeah? Simple as that. Flat bars, gauge, who cares, doesn't matter, it's for that mine. It's whatever the wagon was made to for that particular mine. Obviously, by the time the 1700s came around, they were doing a lot more shifting of ore and coal and stuff, and they needed to be a bit more efficient than that. So they developed these things called plateways. So L-shaped or U-shaped things that unflanged wheels can roll along. Again, the gauge is whatever you fancy doing at the time. There's a couple of photos of some old trackways. The one on the left there is from Bliss Hill. And you can see there's a little U shape, and the wagon rolls in the middle, and then the one to the right here is a reproduction that was made at Coalbrookdale. So if you ever go up to it, have a look, go and have a look. The thing about these is obviously the unflanged wheels And the good thing about that is that a level crossing can be truly level. Because the wagon goes along the trackway, gets the level crossing, comes out of it, and it goes back in the tracks on the other side. So it truly is level. The big problem is you get a stone in this U shape, which is probably fairly likely, you're going to get a bump at best. You get derailments, you get a lot of wear, dirt and so forth. Okay? But that's how it was until a gentleman called George Stephenson came along and made the first true railway, if you like. And he decided to use rails on edge rather than flat bars, and he put flanges on the wheels. And I'll come to why the flanges are on there later. Okay? Now the original plateways up in Yorkshire or whatever it was he was building this were 5 foot centres. And these bars are 4 inches wide. So that makes his gauge from the inside of there to the inside of there 4 foot 8 inches. That's where it comes from. Okay? Straightforward? Where does the 8.5 inches come from there? So Stephenson was contracted to build 2 railways, the Liverpool-Manchester and the Bolton-Lee railways, both of which were specified on the specification document at 4 foot 8 inches. He built them, and then he had a problem when a wagon wanted to go around the corner. He just kept binding. So he did the simple expedient and moved them apart 1/2 inch. And that solved all the problems. And that's where 4 foot 8.5 inches comes from. The standard gauge was born, as they say. Now, other gauges have developed. So as an example, this is Australia today. So it runs 6,800 miles of 3 foot 6, 10,100 miles of standard 4 foot 8.5, and 1,500 miles of broad gauge, and 163 miles of dual gauge. So they're all over the bloody place. Yeah. Now at the same time, or just after Stephenson was developing his thing, his railways, there was a guy called Isambard Kingdom Brunel, I'm sure you've heard of it, building the Great Western Railway. Now he didn't have any of the hangovers of collieries and plateways or any of that, so he decided to do his gauge at 7 foot, which gave additional stability, much better in the long run. We wish we'd stuck with 7 foot for the entire country. Yeah. So why didn't 7 foot last? Well, basically what happened was all of the pioneers, so up in Yorkshire, one up over here, one over here, one over here, building individual little railways, they all basically did what they wanted. And then they started to expand to a point where they started to join up. Now when you join up and you've got different gauges, you get like this. This is Didcot. So you've got standard gauge on this side, and you've got broad gauge on this side. So they had what they call transfer stations. You literally come on one railway here, and you get out of that carriage and you go on this one, and drive off on the GWR. Obviously not very efficient, not good for freight. Will have to be manhandled across. In 1845, they set up a Royal Commission for Railways to decide what they were going to do going forwards. And in 1848, they had the Railway Regulations Act, and they picked standard gauge 4 foot 8.5. And the reason for that is there was 8 tons more of that than there was of Brunel's 7 foot. Simple as. So we have one choice. We either make GWR change their 1/8, or make everybody else change their 7/8. Bit of a no-brainer, really. There was no expectation though that GWR would rip up all their track and change the standard gauge, but they did it anyway. Took them 20 years, cost them £800,000 in 1850, which in today's money is £108 billion. GWR never made a profit as a result. So one of the other side effects, if you like, I suppose, of joining up all the railways is railway time. So before all the railways joined up, every individual town had its own time. There was no universal nationwide time. We didn't need it. the time would be based probably typically on the clock tower in the middle of the town square. And, I don't know, Aylesbury would have a different time to Hemel, which would be a different than St. Albans, and so on. Doesn't matter. Once you've got a universal network with a timetable, you can't have that anymore. You've got to know the time here is the same as the time there. And obviously they were all set to be Greenwich Mean Time. So go back to gauge. Any gauge under 4 foot 8.5 is called narrow gauge. Okay? The one you're probably most familiar with is what we call narrow gauge, which is 1 foot 11.5 inches. As you might find at the Festiniog Railway and Welsh Highland Railway.
When they converted the broad gauge to standard gauge, did they keep one rail and then move the other one across?
No.
Or did they rip the whole thing?
I think that, I don't know, to be honest. I think they ripped the whole thing up.
Less, couldn't it?
Yeah.
Half the price.
Well, you could reuse the rail, but it still cost an awful lot of money in labour.
I think it was a different section, wasn't it?
Yeah, I think it was different sections. Well, yeah, I think you're right. I don't really know the answer to that, I'm afraid.
It was done very quickly, though, wasn't it?
It was done within 20 years. They did the whole thing in 20 years. So this little railway, which I know is very dear to Mick's heart, one day I want to do a talk on this. You never know. Might talk him into it. Actually predates Stephenson's railway, but originally it was a horse-drawn and gravity-fed, so it doesn't really class as a railway at the time. One little thing, notice the spelling? How many F's in Festiniog, Mick?
Two.
So why do we use one?
That's the anglicised version.
They've only got 1 foot 11.5 inches to fit it in.
No, the Act of Parliament that was raised in 1832 to allow this railway to be built only had 1 F in it. They misspelled it. Believe it or not. Anyway, little aside. So technically it should be called that, not 2 Fs. So as I said, there are other gauges are in use around the world, like I mentioned in Australia. So New Zealand, South Africa use a 3 foot 6 inches. In Switzerland, they have 2 gauges. So in the mountains, they use 1,000 millimetres. And in the lowlands, near the lakes and stuff, they use standard gauge. And they have a good way of dealing with it. How to make this work. Talking with Mick before, he reckons this is probably the only time it ever worked. So, enough about history, let's talk about some proper engineering, shall we? So as I said earlier, railways are a result of thousands of small individual innovations. Yeah? So the question is, how do you move upwards of thousands of tonnes of material or passengers per vehicle without tearing up a road? It's not going to work on an asphalt or a gravel road or whatever. So the answer is you coat the road with steel. Now the trouble with that is steel is expensive. Yeah? So you can't really use a flat ribbon of steel. So what we do is just 2 narrow rails. Obviously directly below the wheels. Likewise, you can't use rubber tyres, because if you use rubber tyres, the tyre deforms, and that wastes a lot of energy. Yeah, so we put, and increases the rolling resistance quite a lot, and that resistance adds up. So we use steel wheels as well on steel rails. And as we all know, it's not as simple as just sticking a steel wheel on a steel rail, because you've got a problem of curves. Doesn't work very well, does it? So you have to have some way of keeping the wheels on the rails. Anybody want to tell me what that is?
Combing angles.
Flanges.
No, combing.
Flanges.
Yeah, combing angles.
So we all have, all railway wheels you'll find, pretty much all of them anyway, except for some of the very old, very big wheeled locos, have flanges on all the wheels. And that guides the wheel as it goes round the corner. Now the reason the flanges are on the inside rather than the outside, if they're on the outside and one side lifts, it can still derail. If it's on the inside and one side lifts, it can't. Ever thought of that before? Now one of the problems with flanges though is they rub on the inside of the rail as you go around a bend. So you're probably familiar, if you've ever lived near a railway, of that squealing noise. That is the flange rubbing on the inside of the rail. That is friction. Friction is not good where you don't want it. Okay? Obviously, tighter the curve, the more rubbing you're going to get. So one of the things that they tend to do is on tighter curves they use harder rails, otherwise the friction wears it away. But there's more than just friction at work here. Pretty much all wagons, locos and carriages have what they call a wheel set. So there's a fixed, two wheels on a fixed axle. And the reason they do that is because of the loads that these things are trying to transmit through to the rails. If they were independent and a bearing wouldn't last 5 seconds. Okay? The trouble with that is that the wheels turn at the same speed. Yeah? And when you're going around a corner, as you can see, the outside track is longer than the inside track. Yeah? Now obviously if you've got the same diameter wheel, one of them has got a slip. Whether it's the inside or the outside, doesn't matter. One or both of them, it's got a slip. Something's got a slip. And sadly the flanges can only do so much to keep them on the rail. And the answer to this is, as Roger told you just now, is conical wheels. Okay? You have a look at this. So the answer is conical wheels. It's wider on the inside, narrower on the outside, and that tends to self-centre on a straight track, as you can see. Yeah? Because it naturally wants to fall down. The one outside wants to fall back to the middle. So it wobbles like this, sinusoidal, backwards and forwards, self-centering, basically. You may, if you've been on a lot of train journeys and concentrate, actually feel that happening even today. You can find the whole thing sways from side to side very gently. Right. And where it really counts, though, is on a curve. So on a curve, the wheel gets pushed to the outside. Okay, so this now gets bigger, and this gets smaller. You see that? So on the outside of the curve, this wheel will travel further than this wheel will travel. So that you don't get any slip. Typically that taper angle on the thing is about 1 in 20. So the outside of a typical wagon or carriage wheel is about 1/4 of an inch bigger than the inside. So smaller than the inside. Yeah, it's not much. Obviously the size of that cone, to avoid slipping, will affect the maximum radius you can allow. So some sharper curves do actually have wagons with steeper cones on them. Part of that problem can be solved with bogies. You know, you can get tighter curves by using a bogie. This is basically a roller skate under each end of the coach. Obviously it can rotate independently, and that means it can get round tighter curves. Obviously it also has the benefit of lots of really stuffed springs and stuff, which makes the ride a bit better. So let's talk about the rails themselves. I'm sure we're all familiar with the shape of a rail. Don't have to be this shape, they could literally be anything. It could be a flat bar if you want. So why are they this shape today?
Efficiency of steel.
Well, basically weight. equals cost. So weight is money. So there isn't a piece of iron on there that doesn't need to be there. Okay? Because weight is money. So you've got the business end, the head. That's where it takes all the punishment, where it takes all the wear. So that needs to basically be as big as you can get it. Because the bigger you make that, the longer it will last before you need to replace it. Because it wears away. In the middle is the web, because you need to raise that top bit up to give space for the flanges and to make sure that you clear any debris that might be on the rail. And then you've got the foot, which is distributing those massive loads down into the ground. Fundamentally, this is an I-beam. We're all familiar with I-beams. They're all used in construction for carrying heavy loads and so forth. Yeah? Now, even steel on steel deforms a little bit. You're familiar with a road tyre squidging. Well, imagine that with a steel. It's just a lot less. The actual contact area, this contact patch, on a typical loco, is the size of a 50p bit. That's as big. So that's a wheel touching a rail. Okay? Bear in mind that that has to carry the entire weight of a train. I'm going to go back and see if I can play this again. Now, because the wheel is conical, okay, what happens, you can see this here, is that the wheel is travelling at different speeds as it goes across. So in the middle is the neutral speed, and here it's getting different speed, and here it's getting different speed. So there is still some slip, even across the sides of a 50p bit. Yeah? And what that does is that leads to grinding. So the wheel or the rail is getting ground together because they're slipping, which we'll come to a lot more later. And obviously, as they grind themselves away, the wheel starts to conform to the rail. Instead of it being a 50p bit, it's a lot more. And that has the bad news. That wants to try and raise up there, and if you go through a set of points, that might try and follow a different route. Yeah, so a lot of wagons and carriage wheels are designed to be remachined back flat or back to a cone. Or you make this bit a lot heftier so that it can take a lot longer before you have to change it. You make this out of harder material. All of these are compromises that you can pay more, get a longer performance, etc. Yeah, so it's about a compromise, which is the right way of doing it. Which is, you know, you pay your money, you take your choice. In the old days, rails used to be made in 60-foot lengths. Now, obviously, you've got to join them together, using these things, fish plates, and that led. I'm sure you're all familiar with the old clickety-clack.
Yeah.
As you go along a railway, every time a wheel goes over that joint, it goes click-clack, click-clack. But you're bearing in mind, yeah, that most carriages have 8 wheels. Trains, certainly in America, could have hundreds of coaches, or at least hundreds of wagons. That's an awful lot, you know, and the train journey can be thousands of miles long. That's an awful lot of clicks and a lot of clacks. What is the actual click and the clack? That's a noise, and in engineering, unwanted noise is waste. Okay? On top of that, every time a wheel goes over that, it goes dump, and it wears out. You imagine a train of hundreds of coaches, hundreds of miles, every one of those joints has got to make sure that every one of these nuts is tight. That is a lot of money being spent on maintenance. And try as they might, we've never designed a joint here that is going to be as rigid as a solid rail. So the answer to that is what's called continuously welded rails. So you'll find pretty much, certainly all the main lines and probably most of the branch lines in this country now, use continuously welded rail. I'm sure there's still some of the old stuff out there. But, continuously welded rail, basically, two ends of the rail, of sections of rail are put together and then welded together. And they either weld them with arc welding or thermite welding. So I've got a video here of thermite welding. It was quite interesting. I was watching this earlier and I thought, this is two different videos spliced together.
This is a
See what I
video
mean?
shot by a railway worker, recording the process of welding to rails by thermite.
Different guys.
Next, let's take a look at how
But here-
railway tracks are welded. This is a section of railway located
So
in
it's very
mountains. Due to the impact of rock rolling, this section of track was severely damaged and needed to be replaced and maintained urgently. First, the workers used a track cutter to cut off the damaged track and then move the new track. The workers used crowbars to lift the new rails onto the wooden TIs, making sure the tracks are properly aligned. They then use a chisel to check if the gap between the two ends of the rails meets the required standards. Once the rails are in position, they clean the ballast under the track with homemade steel claws to make room for the welding mold. Next, the welding mold is installed. The red bricks the workers hold are graphite sand molds made from heat-resistant materials. It can withstand temperatures up to 3,500 degrees Celsius, which is crucial for the thermite welding process. Meanwhile, another worker prepares heat-resistant sealing mud on burlap bag. Once the mold is ready, workers carefully adjust the position of the rails with a measuring tape and hammer to ensure a precise fit. After aligning the tracks, the sand mold is placed between the rail ends and secured with a homemade locking tool. Then, the sealing mud is filled into the mold to prevent molten aluminum from leaking out during the welding. Once the mud is in place, a support is installed beneath the mold to ensure it is sealed tightly. After setting up the mold, workers bring over a heating device and connect the fuel pipe to the sand mold. They then ignite cardboard and use flamethrower to preheat the mold. This step is called mold preheating, which helps prevent the mold from cracking due to the extreme heat generated during welding. During the preheating phase, workers prepare the thermite welding compound. The welding agent consists of aluminum powder, iron oxide, and graphite. The prepared compound is poured into a high-temperature reaction furnace. Workers then lift the furnace to the welding site and place it over the preheated sand mold. The workers strike a match to ignite the welding compound in the furnace. As it ignites, the furnace releases white smoke and intense flames, beginning the welding process. In this process, aluminum powder reacts with iron oxide, creating a chemical reaction that produces temperatures over 3,000 degrees Celsius, melting the metal into liquid iron. This molten iron flows into the gap between the rails, welding them together. Graphite helps control the temperature and stabilize the reaction. Thermite welding also involves physical principles. Due to the difference in density between aluminum and iron, the heavier molten iron flows into the gap between the rails, while the lighter molten aluminum rises and flows out through channels in the mold to the outside of the tracks. As the fire went out, the welding process is nearly complete. The workers remove the furnace, dismantle the tools securing the mold, and clean off the hardened sealing mud around the area. While the weld is still red hot, they quickly bring in hydraulic equipment to push the two rail ends together, a process known as rail squeezing. This helps achieve a tight weld for the best thermite welding result. After the rail squeezing, workers use tools like axes and hammers to remove any excess material from the weld. Finally, they use a rail grinder to smooth the welded area, ensuring the two rails join seamlessly. And that's it, the entire rail welding repair is complete. If you like this type of video, please like, subscribe.
Best one I could find. But as you see, there's definitely two sets of workers there. Which is a bit weird.
Killed some of the others in the other process.
Now, one of the things, or one of the problems with continuously welded rail, is that steel, like all materials, expands and contracts with temperature. Okay? So the coefficient of expansion of steel is that very, very small number there. Okay? But if you take a rail that's 100 kilometres long, that's 1.2 metres per degree C. That is a very, very large amount. Your rail has suddenly got bigger. Yeah, if it gets 10 degrees hotter, it's expanded by 12 metres. And then you end up with buckled rails. like that. So how do they overcome that? Well, I'd like to demonstrate this with 2 volunteers, please. Come on, I want some audience participation. Can I have some volunteers from the audience, please? Mike, Swine, you can hobble up here. Come on, somebody else.
Come on, if I can, someone else can.
Right. So I want you to pick this up, hold it from one end, you hold the other end. Right, what I'd like you to do, very gently, push them together. Push it together. Right, well, that's enough. You'll break it if you go too much. Would you agree that's really easy to do?
Yes.
Yes? Try it now. It's a lot harder, isn't it?
Yep.
So that's what they do. They side constrain it by gripping it in the middle, or on a railway at every sleeper.
I'd like to point out I've seen buckled rails on the old 60-foot lengths in the middle of Sunningdale Station. Literally, they snaked and trains were cancelled because it was so hot.
So one of the most important jobs of the ballast is to stop the rails from moving side to side. Because if they stop it from moving side to side, they constrain it like I did by holding the middle of that. It's a lot harder for the rail to buckle. If you can imagine you do that at every single interval, that's how they stop it. Another thing they do is they paint the rails white. Apparently this is something that Network Rail did last year in the southeast, and they reckon that just by painting the rails white, it reduced the temperature of the rails by 10 degrees C. And obviously if they're 10 degrees cooler, they're not expanding as much.
We'll have to do that on the puffing field.
I suggest the next one actually is
What happens when it goes well below zero then? Suddenly it's all in tension,
it's all in tension.
does it?
If you're unlucky, it
Never
breaks.
gets to yield though.
No, if you're unlucky, it breaks. The other way they do it, and I personally think this is very clever, they make sure that the rail never undergoes compression. So you're pushing that together, you're making the rail, you're compressing the rail, yeah? And when you compress it, it wants to buckle. So the way they do that, twofold. Either they make sure they install rails on the hottest day of the year. That's when it's at its maximum. So after that, it contracts when it cools down. Then when it gets hot, it goes back up to where it was when it's at the hottest day. So it's never getting any longer. Understand? Now obviously it might work in somewhere like, you know, Kansas or somewhere like that. Doesn't tend to work very well in our sunnier clime, shall we say. So what they do is they put this sort of device on. They physically pull the rails together. So they put tension into the rails using massive hydraulic jams. This is quite small, I couldn't find a bigger one. But this is actually just pushing the rails back together during the thermite process. But you can imagine one of these devices but about 10 times as big. It's gripping the rail and it's tensioning the rail, so that when it gets hot and it wants to expand, all you're doing is releasing that compression. So it never ever gets any longer. Yeah? To answer your question, basically the rail gets in tension, but steel's pretty good at handling tension. It's pretty good at handling compression as well, but it tends to buckle. But if it gets, the worst that will happen on a really cold day is it will break. Yeah, and if it breaks, then you get a gap, and they still have to go out and inspect the rails to make sure there aren't any breaks and stuff on cold days. But that is much more preferable than getting that, which causes derailments.
And is there any way of knowing how strong that weld is compared with a normal length of track?
Well, if they've done it right, it will be as
relying
strong.
on that for quite a bit, I thought.
Yeah. Now, obviously, you have to have the end of continuously welded rail at some point. You know, you've got bridges, sets of points, things like that. And obviously, you might want to join to older rails that weren't continuously welded. And to stop the buckling there, they have a simple joint like this, overlapping joint, which allows them to move one past the other with this oblique joint. The other benefit of this is it allows you to be able to put a brake in an electrical circuit, which you might need for signalling and stuff like that. And they tend to use the rails to use as conductors for the electrical signals, for signalling and so forth. And then you've got to put a brake in it.
Got it. When the rail expands or shrinks, does it slip through the rail chairs or does it take the sleepers with it?
It will slip through the rail chairs, generally speaking. So let's talk about ballast. Every single railway has ballast, but not very many people understand why it's there. I certainly didn't until I looked at this, if I'm brutally honest. So what is ballast? Well, ballast is just simply crushed rocks. Typically about 5 to 10 centimetres, roughly, something like that. The important thing is they're all jagged edges. That's the important thing. It wouldn't work if they were nice smooth stones. They have to be jagged edges. Okay? And of a relatively consistent size. So the bed below this rail is typically like that, full of ballast. And obviously it's between the sleepers, around the sides. Their job is to keep the sleepers where they are. Yeah. So what does ballast do? It holds the sleepers in place. It stops them from moving longitudinally. Yeah, as I just explained. It also stops them from moving side to side. It aids in load distribution, so the massive weight that's coming through wheels onto rails has to go into sleepers and then into the ground. So it's all about spreading that load out so it's not in one point, if you like. It provides vibration damping. So as the train goes over, it's wobbling up and down from side to side and all the rest of it. It damps the load of that, which means the passenger's comfort is a bit better. Its main, one of its main jobs is providing drainage. If you didn't have ballast and good drainage, when it rains, the water sits there and then the rails rust. You want to make sure you get all that water away. It also stops short circuits, obviously. It prevents vegetation from growing. So the vegetation has the same problem as water, but vegetation has a habit of dying when it gets too hot or dry or whatever, and that produces compost, which is effectively soil. So encourages more vegetation to come along, and the more vegetation you get, the more it dies and the more mud you get, and when you get mud, the rocks slide over each other. So we don't want vegetation. And last but not least, it's got a very large surface area. There's one more. Large surface area, so it absorbs all the noise that's coming out the train. Again, that's to do with comfort for the passengers. And it minimises what we were talking about earlier about the heat expansion. Now, once it's there, they don't just put the ballast in and say, there you go. As I said, it gets muddy, it gets covered in dirt. So from time to time they clean it. So this is a ballast cleaning machine. You look at the front, it's taking the ballast out from under the track, still in place, goes up here, gets cleaned, and comes back and puts it in. And they do this regularly throughout the entire network.
Must be the express.
That's the dirt going off. Let's just throw it in the head, shall we? You can see that it's sucking it up here. And it goes up into the machine where it gets cleaned, where it comes back down.
There's a chain that runs underneath that scoops it in.
Scooping it out.
Sucks it out.
videos, it can't be that much longer.
It's a very quiet machine,
It is when you turn the noise off. And that's it being put back. You can see it's all nice and clean now. They physically wash it.
I assume it gets vibrated a bit as well to get it well.
Yeah, I think that's what they do. This scrapes it off and then further back here they vibrate it down into it. They do look around, it's a bit banky one there, isn't it? It's not their job, mate. So, chairs. So, Neil's very kindly brought in an example of a cast iron chair, which is dated about, was it 1923 or something?
26.
26, oh, it's got written on it, September 26, I guess. This is obviously the old traditional way of doing it. So what do? They basically transfer the weight of the heavy train onto the rail, through the chair, onto the sleepers. Yeah? And they are connected onto the sleepers, traditionally like the one there. These are the wooden sleepers, and they're connected with spikes hammered in, or with bolts. They're held in place with a spring clip. There's various different designs. I think this is the old-fashioned way, which is a block of wood. A wooden block. And I've seen different designs. You get 2, 3, 4, 6 bolts, depending on how much work they've got to do, where they are, and so forth.
Is that done on the inside or the outside of the rail?
Outside.
I've noticed on railways with old-fashioned sleepers that those keys are very often only half in and half out. And I've always wondered whether that's because they're almost falling out, or whether there is a reason they only put them halfway in.
Don't know. Mark?
I think they're falling out.
No.
There you go. I just remember there was a big weight guy used to come along with a long hammer and just whack it back in.
It's so until they're tight. That's the idea.
Yeah, as long as
They're not that
yeah.
tight if they're sticking out like that. If they're all the way in, they might be loose. So
Yeah,
that's
fair enough.
They tend to fall out due to braking,
Yeah.
and then the rail gets pulled along.
They're just spring steel, so
they're
they could well easily break. So, what does the chair do? Obviously, as I said earlier, it distributes the weight from a very, very heavy train through the rail, through the chair, onto the sleeper. They obviously make sure the rail is held in place and that the gauge is maintained correctly so they don't space apart. Modern sleepers, on the other hand, are concrete and have built-in chairs, effectively. And then they use these spring clips, which are nicely coloured blue on this one, so you can easily see them. But they're not rusty. But that's kind of the modern way of doing it, if you like. So let's have a look at sleepers. So traditionally, made out of wood. The trouble with wood is they either rot away, or you've got to coat them in some sort of environmentally unfriendly material to stop them from doing that. So we don't tend to use many of them anymore. Most sleepers in this country are now made out of concrete, although they do still use steel and plastic on places like bridges, stuff like that, where the concrete would be too heavy. These last a lot longer and also a lot more rigid than these, so there's a lot of benefits to them.
So how much reinforcing is there in the concrete? Because they're obviously reinforced, otherwise they fall apart.
Here is a video of concrete sleepers being made.
Ah, great.
Where you'll see how many reinforcing rods there are inside each one.
Oh, lovely.
this machine stretches the wire. There's the chairs and the springs. So what do sleepers do? Well, they distribute the load from the rails to the track bed, like the chairs. Again, they maintain the gauge. They resist that longitudinal movement we talked about for the thermal expansion. And they resist lateral movement as the train goes around the curve. It's obviously wanting to push the track further out. And they help to electrically insulate, I can't say those words, insulate the rails for things like points and so forth.
I think they might have one other use. If you go to Hemel Hempstead railway station, there's a subway that goes under the track. There's 4 running lines, and I noticed that it goes from concrete sleepers to timber sleepers past the subway, which I think is probably acoustic.
It's noise.
Yeah.
Noise.
Yeah, they've put concrete ones at Watford now with the subway, and it's noisy as hell through the subway.
Yeah.
But traditionally, whenever you've got a subway or walkway, they use wooden sleepers still.
That makes sense.
Do they have more sleepers round the curves to, per foot length?
Not that I'm aware of. Unless you guys can tell me any different, but I'm not aware of it.
It's a standard.
It's a standard spacing.
But it's a spacing on the inside rail or the outside rail?
Yes.
That's a big point, I think.
In the middle.
Purely for noise, noise of the subway.
Right, so I don't know whether we want to break for tea now and a chat and come back for the bits I've got afterwards.
Good question.
Go on.
A rail's ever is the profile on the top of a rail ever reground in situ rather than...
Yes.
Okay.
They've got trains that go for the night and they just showers of sparks if you're anywhere near them. Obviously they know that where they're doing it. But yeah, it's like literally a grinder that will reprofile the top of the rail.
Presumably you can do that times before you have to replace the rail itself.
Yes.
It goes down to that.
Depends on how big the rail was in the first place.
Yeah.
They put bigger rails where they expect to get high wear.
Okay.
So that allows them to regrind it more often.
Grinder machine has a nifty water spray, runs in front of it before it comes on and grinds, so it doesn't set fire to the bushes. But do that round up.
I have a little family story about thermite, if you like. My dad, doing a joint civil and mechanical degree, was at a lecture. They described thermite and how to make it. So he and two mates went down to the chemie lab, got a crucible, put the aluminium powder, iron oxide, and then a cone of sodium chlorate to ignite it, and then a magnesium fuse to ignite the sodium chloride. Unfortunately, he got some chlorate onto the fuse, so instead of burning down slowly, it went zoom, and he only had time to duck below the bench as this lot went up. The place filled with smoke. When it stopped burning, there was no crucible and a bloody great hole in a teak bench. They scarpered.
Clive?
When British Railways ventured in, you had Rail Track, a private company, and the Tops, and that was in the late 1990s. And then you basically Network Rail was set up after the Hatfield disaster. But in the early 2000s, you had the train operating companies putting claims against Rail Track because their rails weren't maintained and they were wearing out their wheels. And of course it went the other way.
Yeah.
Well, your wheels were wearing out our rails. Yeah.
The 4'8.5", which is 1435 millimetres. The modern standard now is they've gone up by 1 millimetre.
Does it? Yeah.
And they've cited in Austria, I think they've gone an extra minute. It's to stop the excessive wear.
Yeah.
So,
Yeah. I mean, if you think about the amount of engineering that is going in on a daily basis to the rail profile and the wheel profiles, they're messing around with that all the time to try and get a better overall compromise, because there's lots of different compromises.
I don't think it came to anything, because you can imagine this view that can come out of that.
Okay. So everything I've been talking about up till now is the physical stuff on the ground. There's a lot more to running a railway than just the physical stuff on the ground. You've got to have locomotives and all the rest of it to pull this, and they're limited in power. So we'll come to that after the tea break, if that's all right.